So yeah, welcome everybody to the main night of the 2024 Festival of Astronomy and Space. We've got a wonderful keynote speaker for you shortly, and then we're going to try and do something different. In previous years, when the moon has been a little bit more friendly, we've done some observing outside. Tonight it's nearly full moon, and so therefore we wouldn't see very much, in all honesty. So Duncan, who just said goodbye to the band there, is now getting in his car and he's driving to our observatory up at Mount Kent. And when we've finished this talk and when we've had questions, we're going to do a live cross to there and do some live observing with the telescopes there. So you get to see what it's like to see our wonderful Queensland sky through the big telescopes we have here at the uni. So a little bit different, but hopefully that'll work really, really well. I would like to recognise the lands that we're stood on here. I take great pleasure in the fact that we live on a continent that is home to the oldest astronomers in the world. There is strong evidence that people have practiced astronomy here for at least 70,000 years, and my colleagues who work studying Indigenous astronomy tell me that recent research is pushing those dates back closer to 100,000 years. So we're part today of that storytelling and that knowledge and wisdom of our place in the universe, stretching back for this immense amount of time. And it's a great privilege to me, therefore, to be on land where my personal passion, the subject I study and that I love so much, has been such an integral part of life for such a very long time. And so I always feel it's very important to pay my respects to elders past, present and emerging from all across this wonderful island nation, but particularly from the local peoples, the Gayabal and Jarawar people. With that all said, I'd like to introduce in a very brief sense our wonderful speaker for tonight. We've got Rebecca McElroy, who is a Women in STEM fellow with us here, and she's one of the world's leading researchers studying objects that are far, far further away than what we normally talk about at these festivals. We always get wonderful questions, particularly from some of the younger audience members, about galaxies and the distant universe, and we all kind of scratch our heads. We've now got the expert. So with no further ado, I'll hand over to Rebecca, who can tell you all about her passion. Thank you.
Thank you for that lovely introduction, John T. Yes, I would also like to acknowledge the traditional owners of this land. As always, we are on unceded Indigenous land, and I would like to pay my respect to Indigenous elders past and present of this country. Yes, so yeah, my name's Rebecca McElroy. I am a fellow here, which essentially means they let me do whatever I like, and they pay me, as long as it's science, I should say, as long as it's science. And they pay me to do that, which is great. I bet you're all thinking that I look more like the type of person who's gonna be some millennial who's really into astrology and talk about Mercury being in retrograde. And I'll forgive you because you're right. I have come all the way from West End in Brisbane tonight. Okay, that joke doesn't land in Toowoomba. Alas, I had to give it a crack. So, but anyway, I promise I'm not going to make any predictions about your love life tonight. I'll save the tarot cards for later. So today I'm going to be talking to you about how galaxies collide. And we'll start with, where are we? Well, we're in Toowoomba. But galactically, we are in a galaxy called the Milky Way. And this is a beautiful image here of the Milky Way. It's this beautiful band of stars and dust and gas across the night sky. And if you've been lucky enough to step outside in this much less light polluted than where I live, you'll be able to see this. So the Milky Way is a collection of about 100 billion or so stars, much like our own sun, and is approximately 100,000 light years across. So really big, lots of stars. We live out in the suburbs. I like to think of it that way. We are out in the Perseus spiral arm, which means nothing to you. But you can think about it like we are in Toowoomba, to the center of the galaxies, Brisbane. We are out on the edge, you know, it's quiet out here, peaceful. What's our galactic neighborhood like? I'm going to be talking to you a bit about the galaxy next door. And I'm not talking about the tiny little galaxies that you might have spotted in the sky if you've looked quite closely. Those are Magellanic Clouds. Those are currently kind of falling into our galaxy. And it's very cool that we can see them. I bet if we drove out of town a bit, we would be able to see them. They kind of look like little smudges. But I'm going to be talking about our nearest kind of big galaxy. And that's called Andromeda for mythological reasons, but I won't go into that. So this galaxy is 2.5 million light years away, which again, that doesn't mean very much, does it? But because I'm a very serious scientist, I happen to know that that's 23 quintillion kilometers. And I did Google that, so I didn't do the maths. But in addition to being our nearest neighbor, it's also hurtling towards us at about 400,000 kilometers an hour, which is pretty fast. It's actually faster than a speeding bullet. So if we went out, maybe not tonight, because the moon is full at the moment, so that tends to pollute things a bit. But if we went out in about 2 weeks and cleared all the clouds, we looked up, we would see this beautiful band of stars that is our home, the Milky Way. So that's this here. And then if you kind of squinted a little bit, you would see this little smudge, and that is Andromeda. Over time, this smudge is going to get bigger and bigger and take up more and more of the night sky as Andromeda comes towards us. The Milky Way might read in its horoscope, you're about to meet someone who's really going to shake things up, and it will do that. So when these galaxies collide, it's a very turbulent period. All this gas and stars is going to get kind of thrown around and thrown together, and you can see all these little hot spots that are going to start appearing. That's bursts of star formation. So when all this gas is thrown together, you get these pockets of star formation, and it'd be really cool. It's going to look really interesting, much more interesting than the night sky at the moment. And then they'll start to kind of interact a bit more and eventually settle down, peaceful, quiet. All the gas will have run out, all the stars will have been formed. Horoscope might say how to spice up your love life at this point, throw another galaxy at it. But you might be thinking, Rebecca, do I need to be worried about this? What's this going to do to Earth? We've already got enough on our plates thinking about climate change, are we going to have World War III? What's going on with all these adorable moo-dang animals on TikTok? So we really don't need something else to worry about. And I'm here to tell you, you don't need to worry, because this is going to take about 7 billion years. And I don't know about you, but I am unlikely to make it to my 7 billionth birthday. Nothing healthy living can do to get you quite that far. So why do I study these things if it takes 7 billion years for it to happen? How am I supposed to study that? I don't live 7 billion years. So how can I actually study this phenomenon? And the answer, as with many things, is with computers. And so we can speed all this up in a supercomputer. So I'm sure some of you have seen that we can simulate galaxies in supercomputers. And essentially what they're doing is they're just putting a bunch of particles in a box and seeing what happens and evolving it for effectively billions of years inside a computer. And we can do this for merging galaxies, like what will happen to the Andromeda Milky Way system. And so what I've got here down the bottom is some snapshots of what that will look like. And this means we can skip all the boring parts. There's no like intergalactic traffic lights. There's no meetings that could have been an email. It's just the good stuff. So what I've got here down the bottom is time. And you can see we've got two galaxies that are kind of starting to interact and then coalescing, calming down a bit, and then finally forming this stable system at the end. And this is just the axis of time over here. And this is what I like to say to all of my colleagues who study exoplanets, which are just these little dots. Cool pictures, right? It's a great reason to study galaxies. Yeah, so that's what I can do. And additionally, we can play with these parameters. Now I'm just going to come forwards to see how this looks. So what I've got down the bottom is 3 of those simulations run with slightly different parameters, just looping. And you can see that they're showing slightly different properties. So we can choose what we want these mergers to look like. I can initialize the galaxies to have different sizes. I can change the orientation that they're coming at each other at. I can change the speed of how quick those galaxies are going. And it's like The Sims, but for galaxies. So you can kind of play with it and watch it happen in a very sped up version. Just to kind of give you an idea of this life cycle idea of what happens throughout a galaxy's life is we start off with 2 spiral galaxies like us and Andromeda, and they begin interacting. There's a lot of gravitational forces and torques that happen throughout this period that I will not go into in detail. Don't worry, there are no equations in this talk. And that drives gas into the center of the galaxies, where it can be used as fuel for the central supermassive black hole. And as I said before, this triggers the formation of pockets of stars. Then, as you can see here, this is being driven out by that supermassive black hole all the gas either gets used up, turns into stars, or chucked out of the galaxy, and we're left with kind of calm, aging galaxy at the end. So in addition to looking at this with simulations, the alternative is we can't look at our own galaxy because it's all happening too slowly. Additionally, it's very difficult to see what's happening from inside a galaxy, right? So you can think of it like if I'm a scientist who studies forests, but I'm inside a forest. It's very difficult to see the forest for all the trees. So you can do loads of interesting stuff on the Milky Way. You can study populations of stars, but trying to study it as a whole galaxy is very difficult because you can't see most of it. Most of it is obscured. The alternative is look to external galaxies. And that is also what I do. So what I've got up here is some beautiful images that my student Nicole made this week. Thank you, Nicole. I think she's online. And these are just a small subset of merging galaxies that we observed with the Very Large Telescope in Chile, creatively named. It is very large. And what we've done here is Nicole's kind of split up those observations into different colors and pulled out some specifically interesting points. So you can see in this one, we've got those pockets of star formation happening. Same here. In this one, the nucleus is particularly bright. There's probably something happening there. And so we actually have 100 of these to look at. So this is just a tiny sample of what we have. And if I put them all on there, you would have been overwhelmed. But these are very interesting, and I can look at these all as a population to try and understand what's going on throughout a merger. I've kind of outlined sort of why this is important, but galaxy collisions are essentially how galaxies grow. So we think that this is how, in the beginning of the universe, there were these small, kind of clumpy little galaxies. And then over the last 13 billion years or so, those have kind of merged and merged and merged and merged. And now we have the big galaxies that exist today. This drives new epochs of star formation. So if two galaxies merge, previously they might have been fairly quiescent, not doing very much. Then they merge, and they have a whole new bunch of stars because all that gas has been stirred up. So it's a big driver of star formation in the universe. Very importantly, they are very pretty. Good reason to study this type of galaxy. You can make beautiful pictures. It is always nice to have nice things to stare at when I'm doing lots and lots of programming. And I think I mentioned earlier that this can activate the central supermassive black hole. And this is the other thing that I'm very interested in. You can think of it like there's two very dramatic things that happen in galaxies' lives. When they collide with other galaxies, very dramatic. And when there's these big explosions happening in the central supermassive black hole. So we're going to take a detour and talk about this for a little bit. Oh, and here's an example of a beautiful active central supermassive black hole that's driving these huge plumes of gas out of the galaxy. That's Centaurus A, if you're feeling nerdy. So we call these active central supermassive black holes active galactic nuclei. Fairly self-descriptive, does what it says on the tin. But we'll start with, in the center of galaxies, there is a supermassive black hole. The one in our galaxy is called Sagittarius A star. And they are generally millions to billions of times the mass of the sun. So these are really big. This is not like black holes that you've heard about at the end of stars' lives, which are like a couple of times the mass of the sun. These are millions to billions of times that size. So it's a very different kind of scale. Because it's fairly casual here tonight, I thought I would take us on a little historical detour. Because I was talking to another one of my students this week, and I was reminded of how the story of the discovery of active galactic nuclei is actually very cool and very heartwarming. And it has a local component, so we'll get into it. So this is NGC 1068, which is a nearby-ish galaxy. And astronomers were observing this in the early 20th century. and they found that it had these weird lines in its spectrum. So that means it was emitting at weird frequencies, strangely bright, and they didn't know why. And all this emission was coming from a really tiny region in the galaxy. They managed to localize it to something very small in the center. We can figure out the energetics from emission lines, and those told us that these lines were too strongly ionized, so there was too much energy going into this emission for it to be coming from just regular old stars. There had to be some high energy process happening to be generating this type of emission. And astronomers took to calling these things Cepheid galaxies, quite predictably named after some dude. The other way we name things in astronomy, named after some dude, or very descriptive. Concurrently, and this might be a story you're familiar with because most of it took place in Australia, astronomers found a bunch of these weird objects that looked like this, that looked like stars, but were extremely bright in the radio. And if you weren't aware, radio astronomy was essentially born in Australia. If you're ever in Sydney, I highly recommend going to Dover Heights, where there is a replica of one of the first ever radio antenna in the world that was used to detect extragalactic sources. Also, it's a very nice walk, and it's on the coast near like Bronte and Coogee, so it's very aesthetic. They found these weird stars, and then they used Parkes, which you may also be familiar with, which is a radio telescope near-ish Canberra, I suppose. And they used that to localize this object and found that the radio emission coincided with something that looked like a star. Now, like, stars aren't supposed to emit in the radio. That's weird. Why is it doing that? And so if you've ever heard the term quasar, QSO, quasi-stellar object, that's where this comes from. So quasar is the final one we settled on, but these were originally called quasi-stellar objects because they looked like stars, but weren't. When they finally got spectra of these objects, so when they managed to kind of split the light into its components for these objects, it looked like nothing they'd ever seen before. Didn't look like any star, didn't look like any galaxy. It looked weird. Actually, it looked like this. So this is the only thing that is like very sciencey, but this is what a spectrum looks like. This is brightness, and this is color. So this just splits up how much light is coming from each color band. And when you have these spikes, it just tells you that there's an excess of light in that band, and it's coming from a specific process due to a specific transition inside an atom. So don't think about that too much. I promise that's as sciencey as it's going to get. Now, there's going to be a lot of words on this, but it's because I thought they were quite nice words. Don't read them. I'll just read them to you, so don't stare at it too hard. So Martin Schmidt is a Dutch astronomer who was pioneering in this area. And so one day he was at work late on a Friday night, like I am, I suppose, and he said, I decided to look with an eyepiece at this spectrum, and it suddenly dawned on me that if out of the 5 lines I ignored 2, then the other 3 seemed to be regular in spacing and decreasing in intensity. Then I did something I'm not an expert in. I decided I would make an energy level diagram. So if you've ever done chemistry, if you see emission lines that are regular in spacing and decreasing in intensity, that sounds pretty like hydrogen, if you're familiar. And if you're not, then that's also fine. And so he did that. And what he found was at first puzzling. These signatures, or spectral lines, did not resemble any of those known elements. He stared at the graphs for weeks, pacing the living room floor, and then he realized the expected elements were all there, but they had shifted toward the red end of the spectrum, an indication that the object was moving away from Earth, and fast. Once he knew the speed, 30,000 miles a second, Dr. Schmidt could calculate the object's distance. His jaw dropped. At about 2.4 billion light years away, 3C273 was one of the most distant objects in the universe from Earth. That distance meant that it was also unbelievably luminous. If it were placed at the position of Proxima Centauri, which is our nearest star, about 3 and a bit light years away, it would outshine the sun. And so my favorite part of this interview is that after he discovered this, he went home and said to his wife, "Something terrible happened at the office today," which I think is wonderful. They discovered this, and very rapidly, things progressed. It was a bit slower then because they didn't have email, of course. But letters flew around the world, and many more of this type of object was discovered. And if you're a big nerd like me, then this is from an NY Times article. And the quotes directly are from a recorded interview that Caltech did in about 1995. So if you feel like digging into that, that's where I found it. So they finally realized that these two classes of objects were actually the same thing, just differing in brightness. So they're all active galactic nuclei. Some of them are just really far away and really bright, and some of them are nearby and less bright. They also found that the emitting region, where that kind of very bright light is coming from, is so small that no process other than accretion onto a supermassive black hole could explain that level of luminosity. Can't be stars, can't be gamma ray bursts, can't be any of these exotic things. Has to be accretion onto a supermassive black hole. So these all now fall under the term active galactic nuclei, which I described earlier. So we're back from our tangent now. Yeah, so we've already said this. So you might say, Rebecca, that sounds ridiculous. Like, that's so bright, so far away. Is this real? Can we confirm this? They're black. How do you see them? This is how you see them. So what we've got here is the orbits of all the stars close to the center of our galaxy, tracked from like the 80s until about 2020. And you can see that they're all suspiciously orbiting around nothing. And that nothing is Sagittarius A star. And based on these orbits, you can calculate the mass of the thing in the center, which is 4 million times the mass. Oh God, that's horrible. I'm sorry, that is a formatting error. I was experimenting with a new piece of software today. I don't recommend that. So 4 million times the mass of the sun. And if you were paying attention to the news in 2020, you might have seen that this actually won the Nobel Prize. Yay! Which is very cool. So there is a supermassive black hole in the center of our galaxy, kind of thereby confirming that that can exist, and therefore we can assume that this is what's going on in other galaxies. Unfortunately, our supermassive black hole is not active. I guess unfortunately for me personally, but I suppose you guys don't mind. So really, I should have been around about 100,000 years ago. And then that would have been a better time. So now I'm going to kind of describe what is a supermassive black hole. Where is all this light coming from? What we've got here is, in the center, the black thing is a black hole. And then around it, we have an accretion disk. And what an accretion disk is, so you can think of this like a black hole is a plug hole. And the accretion disk is the stuff that's waiting to fall down. So the easiest way I can think of to explain this is, you know, if you throw a bucket of water into a bathtub, it doesn't all immediately just straight down the drain. First, it kind of spirals around and splashes about, and then it goes down. And that's essentially what's happening in an accretion disk. Apart from it, there's much more complicated physics, and it's all very weird and very hot. But essentially, it's a bunch of stuff spiraling before it goes down into the black hole. And it's superheated. And so it's emitting across the entire electromagnetic spectrum. So these things are enormously bright. This can outshine an entire galaxy's worth of stars, just this little thing. But we think that around this accretion disk, there is a torus, which is kind of like where a bunch of dust has built up around the edge of the accretion disk, and that blocks you from seeing it from some angles. And then kind of scattered around this, this nuclear region, we've got these fast-moving clouds of gas. We've very creatively called them the broadline region. It is because it is where the broad lines come from. We really need to get better at naming things. But these are just fast-moving clouds that are emitting lots of light. And then a bit further out, we have the narrow line region, and I bet you can guess why we named it that. It's where the narrow lines come from, a bit further out. And so the idea behind this dichotomy between these two types of object, when it appears, is that when you have this enormous brightness and this very weird, steep-looking spectrum with these broad emission lines, your telescope is looking like this, down onto the accretion disk. So you're getting all that light directly from the disk and all this light from these fast-moving clouds. But when they're more dimmer and they don't have all those weird features, you're looking through this torus. So essentially a bunch of stuff has been blocked out by this kind of wall that isn't letting you see anything past it. So as I mentioned, this is the most energetic process in the universe and can launch these enormous jets coming out of galaxies. Oh God, it's happened again. I'm so sorry. Oh dear. Okay, I don't recommend Canva as a piece of software. This energy profoundly affects galaxies. It's very important. It's jumping up and down. So this energy doesn't just drive jets. It also kind of propagates through the disk of galaxies. It's like dumping a giant heater in the center of a room. Like it doesn't just all dissipate. All this stuff is going to interact with all the stars and the gas in the galaxy. So in particular, it can stop stars from forming because stars require gas to be cold and clumpy. And if you heat things up, it's not cold anymore. And so that stops stars from forming. I'm so sorry. So this energy is fed back into the galaxy, and we, of course, call that feedback. Now, go away, jumping up and down things. Goodness me. Okay, so studying AGN. So in order to test this theory of can we see feedback, can we see what that energy is doing to galaxies, I study AGN. And the smartest thing to do would be to select the brightest active galaxies in the nearby universe, because the brightest ones, the most energy, you would expect them to have the largest impact on the galaxy. So that's the idea, that feedback should be the strongest in these galaxies. Oh God, I'm so sorry. So we collect data across the electromagnetic spectrum, and we can make more beautiful pictures like this. So what we have here is just 3 examples of active galaxies from the local universe, again with specific types of light pulled out to highlight different regions. And this is from the Close AGN Reference Survey, which is part of a large international team that I'm currently leading, where we've been able to get data from telescopes from across the world. So we've got data from the Anglo-Australian Telescope, which is in Coonabarabran, a mere 6 or so hours away. From ALMA, which is an enormous radio telescope in the Atacama Desert of Chile. Very large telescope, aptly named because it's very large in Chile. And even the Hubble Space Telescope, the Chandra X-ray Space Telescope, and many others that I'm certain I've forgotten. Okay, so I'm going to talk about just one galaxy for a little bit. So we had this whole sample. We've got 40 galaxies. We specifically targeted them because we wanted to look for evidence that the black holes were having an effect on the host galaxy. And when we opened this particular batch of data, we were quite surprised. So this is Markarian 1018. It was supposed to be a bright type 1 AGN. So it was supposed to be one of those ones where we're looking directly onto the accretion disk, all that bright light and those broad emission lines coming from the center of the AGN. But instead, we found that it had dramatically dimmed, and all those really broad emission lines had disappeared, which is really weird because these things, as I said, are billions of times the mass of the sun. You don't expect them to change on a person's like timescale, like it's supposed to stay the same forever. But even stranger, when we looked in the literature, this had actually happened in the 80s before. And somebody who had planned the survey, not me, hadn't spotted that this had already undergone quite a dramatic change in brightness. So now we have this weirdo that doesn't seem to fall into either of these types of active galaxy that we've talked about, and that also is changing between them, which doesn't seem to make any sense. So what could cause this type of behavior? So one thing is obscuration. So simply, you put something in front of the galaxy, then you can't see as much light from it. But like, not so much like this, more as if something had passed very close to the center of the galaxy, because we can still see the whole galaxy, of course. So it would just be something very close to the center, an increased amount of gas and dust in the center of the galaxy, blocking light and reducing the brightness. This, of course, would cause it to dim. But if you ever looked at the horizon, or if you've been around when it's very dusty, you'll notice that dust reddens light, and this is because of preferential scattering of blue light. But we don't observe this to happen. So that tells us that it can't be dust, and it can't be extra stuff along the line of sight. And we confirmed this with other observations with an X-ray telescope, which gets you a very definitive idea of exactly how much gas is along the line of sight to an object, and it hadn't changed. So it's not just that something has stepped in front of it. Now, I'm hoping that this video works. So if a star gets sufficiently close to a black hole, it can be pulled in. And that's what this artist's impression is showing you. So a star has gotten sufficiently close that it can't escape the gravitational pull of the black hole, and it gets essentially pulled in and ripped to pieces and pulled into the accretion disk of this supermassive black hole. And we know this happens. There have been many observations of this phenomenon. It's very cool. But because we have so many observations of it, and because it's a fairly well-defined process, we have a good idea of how this works. Particularly, it causes brightening as the star falls in and is consumed, and then dimming as it kind of runs out of fuel and the star's been eaten up in a very characteristic way. So we understand what that should look like very specifically. Additionally, you can't have this happen for more than a couple of years. All the simulations have shown that a star can't survive that long in this kind of environment. But with Markarian 1018, we see the same brightness over a period of 30 years. So unless you kind of come up with a very convoluted example where you've got a constant stream of stars falling in, that seems like an unlikely scenario. So another alternative is that this supermassive black hole is simply low on fuel. So as fuel runs out, there's less stuff pouring onto the accretion disk. It goes down in brightness. Additionally, that means that those clouds that we saw kind of floating around the accretion disk are no longer illuminated. So you can think of it like you turn down a dimmer switch on a light, then less and less of the room is illuminated. This causes a very specific signature in the galaxy. So as that kind of radius to which we're illuminated comes in, because the gravitational pull is stronger further in, it means the stuff here is moving a lot faster than the stuff here. So that means that we should observe that the lines, those big broad emission lines, should actually broaden as something becomes dimmer. That sounds counterintuitive, but it does make sense physically. And in fact, we observe the opposite. The lines get narrower, which tells us that there's something wacky going on in this system. So the keen-eyed among you may have spotted that this galaxy is a bit of a mess. Specifically, is train wreck, maybe? I don't mean it. So what we've got here is, this is this is the system here, and then you've got a little companion falling in. And then if you look closely, you can see these tidal arms flying off. And so what this means, bringing it back to our earlier work, is that this has undergone a merger. And so you could say, okay, so that might have caused the black hole to activate, but that won't cause it to change on this very, very tiny timescale. Mergers take billions of years, as previously discussed. But if you've undergone a merger, there are two galaxies. What if there are two supermassive black holes hanging out in the center there? Could some interesting orbital dynamics cause that 30-year change in brightness? Or you might have heard about black hole mergers recently. The gravitational wave experiments have been finding these all over the place. Unfortunately, they can't detect things this size yet, but one day. But what happens when two black holes merge is they turn into one black hole, but also there's energy left over. And so we call that a recoil or a kick. And so once the merger has happened, there's this kick of energy. So it could be that the resulting black hole from a merger has this residual energy and is on some kind of strange orbit around the center of the galaxy. And unfortunately, I'm not going to end this in a conclusive way. I'm going to say, what's going on with Markarian 1018? I don't know. This is a particularly interesting system. And I'm still working on this to try and figure it out. In particular, another of my students, Thomas, he's looking at digitized plates from the earliest ones are from like the 1920s, and the latest ones are from 1998. So these are from observatories all over the world have digitized all these photometric plates from before we used cameras on telescopes. And now we're going to try and analyze the data from this to see if another transition has happened, so we can pin down whether or not this is a periodic thing, whether this is likely to be due to some interesting orbital dynamics. But for now, I have to say question mark. Aliens, wizards. My money is probably on something a little bit more banal, I suppose. You can have, so there's all these kind of fun and exciting options where you've got binary black holes or black holes with interesting kicks or merger remnants, but there's also just, we don't fully understand the dynamics of these incredibly complicated and very physically extreme objects. So there could just be some parameter that we're not seeing. There could be something chaotic that we haven't even thought of happening in the center of these galaxies. And yeah, so I'll keep thinking about it. And I've got a long time to think about it because the next big thing happening is in 7 billion years, remember? So Andromeda's not going to show up for a while. So I like to think that hopefully at some point in my career, assuming I continue to be employed, I'll get to find out what happens, what's going on in this galaxy. Will we get to observe another phase change between these two systems? Yeah, so I think that's all I have to tell you about this evening. I'm very happy to take any questions you have. Thank you.
That's fabulous. Thank you very, very much. We've got a microphone runner coming in to take any and all the questions you've got. And I think we've got plenty of time for questions before we change over and do some observing. So I think we've got a hand right up at the back next to the gentleman in the blue shirt.
So I just have a question, just understanding our own supermassive black hole. Mm-hmm. You said that it's not active. Mm-hmm. So is the next activation considered to be when our galaxies merge? Or is it more like it's like a volcano?
Yeah, that's a very good analogy. I think I was having this exact conversation with my colleague earlier. So there are two modes of this type of thing. There's the extreme brightness events where you've dumped a lot of fuel into the central supermassive black hole. And you do need something quite dramatic to happen for that. So a merger, an interaction, something weird going on with the bar, maybe. So our galaxy is barred. That's a way of kind of funneling stuff into the center. So yes, probably the next time there will be a very bright active phase will be when something dramatic happens, e.g. merger. But there's also the stochastic low level, up and down, low luminosity stuff, which we think has been happening as recently as 100,000 years ago. So in addition to the major merger that we talked about, the Andromeda Galaxy, there's also these two small clouds that are falling into the Milky Way. And evidence suggests that stuff had been falling onto the black hole, and it had been in an active period because parts of this stream that's going around the Milky Way was sufficiently bright that it had been shone on by like this big torch in the center. So my answer is yes and no. So we can expect something on a shorter timescale, less dramatic, but big dramatic thing, longer timescale.
What would the black hole be orbiting in the center of the active one that's flashing on and off?
Yeah, so it would be orbiting the center of mass of the galaxy. So perhaps contrary to what one might think, in a gravitational system, bodies aren't actually orbiting each other. They're orbiting the center of mass of the system. So, for example, the moon is not orbiting the Earth. The moon and the Earth are orbiting a point somewhere inside the Earth because that's the center of mass. And so in the same way, if there was a single supermassive black hole inside Markarian 1018 that was still kind of on this eccentric orbit, it would just be orbiting the center of mass of the whole galaxy.
If you've got an accretion disk, it would generally tend to move into a circular pattern. If you had a black hole in an elliptical orbit inside that, then periodically it would be able to grab mass from the inner edge of the accretion disk as it's moving slowly, and then it would speed up around the center of mass of the galaxy. But the ratio of the black hole mass to the accretion disk mass would have to be pretty, the black hole would have to be pretty light in order to move around that much.
So the accretion disk is bound to the black hole. It's not a stationary object. So understanding that system is difficult. And there are people who work on specifically accretion disk simulations, and they're kind of playing with these ideas. But yeah, it's interesting because this system that we've built up, so there's the accretion disk, there's the black hole, and there's the clouds, and there's that dusty torus. The only things that are bound, really, are the black hole and the accretion disk, and to some extent, the clouds. And so are all of those things moving? What happens when that's happening? If there's another large body in that system, again, that can pull things in interesting directions. So really, it's very complicated, unfortunately. And I think something that will really shine a light on this sort of thing is looking at these types of objects with the next generation of telescopes. So things like JWST, which is Space Telescope, kind of Hubble on steroids, that will be able to resolve very tiny things that we're not able to resolve at the moment, or the extremely large telescopes that will be coming up in the kind of 2030s, fingers crossed, will hopefully allow us to see kind of deeper into this, to actually understand what the structure of the inside of the nucleus is.
Have you put in a proposal to use the James Webb Telescope for anything? And if you have, what are you going to use it for?
I haven't. I thought about it. So there's a deadline coming up, which is probably where a lot of our colleagues are, presumably.
I think it's next week, actually.
Yeah, it's next week. My partner is also currently frantically writing a JWST proposal. Yeah, I thought about it, but it's an intense amount of work to put in a James Webb proposal. You not only have to write the proposal, you also have to plan all the observations, which is not normal for a telescope. Usually you get awarded the time and then you do the difficult part of planning the observations. But with James Webb, you have to do it all in one go. And unfortunately, I didn't have capacity to spend the time on it. But I am hoping that somebody else has put in a proposal to look at a galaxy, if not this one, then something similar. And we'll get some really interesting data.
Just putting that in perspective with applying for time, anybody on the planet can apply for time on James Webb. I know the first year that proposals were doable, when it was up there and people could actually get time. One of our colleagues, Chelsea, who's a future fellow here, who's another one of our permanent researchers, essentially, she was one of only 2 proposals from the whole of Australia to be awarded time in that year. So this is one of these things, it's a huge amount of work, but it's also really competitive. And it isn't a case that the applications that don't get up are not very good science. There are more questions that we want to ask than there is time available to answer them. So it's a huge investment, and then you submit it, and then you basically accept to yourself that you will never be successful, because then when you find the results out, you're not disappointed. And if you get the time, you're incredibly fortunate and very, very happy, basically.
Do you know what the oversubscription rate was?
I don't know for JWST. I know for Hubble for a long time it was 6 or 7 to 1. So in other words, probably more for JWST.
I think it was about 15. So the 15 times the number of proposals than they could allocate time for. So it's not very good odds. Not very good odds. But yeah.
We have any more questions in the room? Yeah, we've got one just over here, and then one up at the back. And you've got some from online as well, by the look.
Oh, do I?
Excuse me. I was interested in your modeling that you're doing, and I've been hearing a lot of noises around about variable speed of light and dark matter and dark energy and all those kind of things, which I don't really understand those things. But do they apply to your models, or do you account for those things in your models? And if not, just because I'm a computer nerd, what do you do your modeling in, like languages and things like that?
Yeah, okay. So the simulations I showed you just then are not cosmological. So that means that we haven't simulated the entire universe. We have we call them zoom-ins. So it's isolated 2 galaxies in a box rather than the whole universe. And so that means we save a lot of computational time, and you don't have to spend thousands, millions of CPU hours on this. And instead it's like down to thousands. So we ignore dark energy. We ignore most cosmology, like most time varying cosmology. For that, there is dark matter, because that's quite important in how galaxies interact, because there's a lot of the matter in galaxies is dark, of course. But yeah, the rest of it don't do. Cosmological simulations do account for all of this stuff. And it's a lot more computationally intense. The simulations are usually written in C or C#.
Sorry.
I mean, to be honest with you, I am not the one running the simulations. It's my very clever friends at Caltech who give me access to their lovely data.
Hello. I was just wondering about the dimming with the galaxy you're talking about. Is that something we see in other galaxies, or is it just sort of a one-off?
Oh, sorry, I must have accidentally not said that. So at the time, it was one of 3 that had ever been observed. No, one of 2 or 3 that have been observed to have that kind of back and forth change. And like contextually, we have observed millions of galaxies at this point, so very rare, but also very hard to detect, right? Because how often are you going back once every 30 years and imaging a system? So the rareness is currently sort of in dispute. And I think the real thing that will tell us how common this is when we have large surveys of the entire sky with spectroscopic and imaging. So kind of the one with the wiggly line and the pretty picture on a regular time period. And that's going to be LSST, which is an upcoming survey, will kind of really tell us how common this type of phenomenon is. I imagine it's much more common than we think it is, but this is just, the reason this is such a special system is because we watched it happen, right? So like we were sitting in a room at a university, well, not at a research institute in Germany, and we opened the data and we're like, that doesn't look right. And first we thought that we'd looked at the wrong galaxy or something had happened. And then we did all kind of the due diligence of checking this. And we were like, no, this is not the only other galaxy that is known to do this in a similar part of the sky. This is actually a new discovery. And then we were able to submit proposals immediately to discretionary time on telescopes. So that's where you can apply at any time. So you get to ignore the deadline next week. You just say, this is so cool that we need to use your telescope now, pretty please. And so the special thing was that we got all this data after we had discovered that it happened. So unlike most of these things where it's discovered 30 years later, it's discovered in kind of these big surveys, we actually got to kind of watch this one go down in brightness. So that's why it's kind of special.
I think we've got an online question.
We have
Des?
one that may be from one of your colleagues or rivals, perhaps. So are you ready?
I'm sure.
The discovery of porphyrion, announced a few months ago, seemed to have opened a lot of unanswered questions. For example, why is this black hole jet so enormous, 23 million light years? You familiar with porphyrion? Oh, okay.
If you give us a spelling, I'll Google it and bring up the Wikipedia.
Well, probably you'll get the Greek god. It's the largest jet discovered so far in the universe.
Mm-hmm.
And there's a conversation article about it.
Oh, okay. So what was the question about it? So this is a large jet.
It's a gigantic black hole jet. Why is it so enormous? Why do you think it's so enormous? 23 million light years. Why is this jet so straight? How have these jets been powered for so long? And how do these jets impact the largest structures in the universe?
Oh,
but perhaps
if
once you've digested all that, so how do these kind of discoveries impact your work or research?
Yeah, so don't worry about finding it. I'll just, yeah. So I'm not a radio astronomer. Is my first statement on this. All of the things I look at don't really emit in the radio. So something I didn't tell you is that there's two modes of how active galaxies operate. One is when we see radio, and one is when we don't. And what we think essentially is happening is when you are emitting in the radio, it's at a lower brightness over a longer time. And we call this kinetic mode because essentially what's happening is that atoms are hitting other atoms, and that is what is causing this jet to form. And this can kind of go up and down and go up and down, but because it's sustained over such a long period of time, you can have these enormous jet-like structures form. And then the other mode is what we're talking about here, which is, why can't I remember the word I'm thinking of? It's so bright that when the light particles, the photons, are hitting atoms, it pushes them away. So it's two different modes of how the energy is being propagated. One is through direct photons onto atoms, pushing them because they're so bright. The other is like atoms hitting other atoms. My caveat is that I only look at the latter type. I don't look at radio galaxies very much. But to answer why the jet is so straight, it's a path of least resistance thing. It's like a river. Generally, a jet will come, instead of coming through the galaxy because there's a bunch of stuff in the way, it'll go out on the poles, right? So the galaxy's like this. Instead of trying to get through all this stuff, it'll shoot out the center. And that's just why you get these very straight jets. What type of galaxy is it? Is it elliptical?
I'll scroll down and read.
Okay, if I were to guess, I would say probably it's a galaxy in a cluster, meaning that there's lots of other galaxies around it. So it would have kind of a constant stream of low-level fuel falling in.
NGC 266
would be my guess.
3.
Don't prove me wrong, Jonty. We don't need to look it up.
Look at McElroy. Yeah, well, that looks fairly elliptical. Elliptical galaxy with a gaseous disk.
Oh, there you go.
This is the galaxy in question.
It's as if I knew. Okay. Oh, I mean, the universe is mostly empty space, so the answer is not a lot. It affects the galaxy it's in very much. Especially this kinetic mode has enormous effects on the galaxies it lives in because it's heating the gas in the galaxy, preventing more stars from forming. That's why it's gone this color. Because when something is red, it means there are no young stars. So it's run out of fuel or it's all been heated up too much by this feedback from the AGN. But yeah, so what it will do is it will do this. It will turn the galaxy red and dead, as we like to call it.
That's good. While people in the audience see if there are any additional questions, I'll just put a quick advert out for this website in case people haven't seen it. The Conversation's a website that I've written for a lot, but it's an interesting avenue for researchers to control the message about the news. So it's the articles that are written for the Conversation about everything in research, from history and the arts to politics to science. But they're written by people who are experts in the field and quite often writing about their own work or work that has been done by their peers. So it's a really nice initiative to try and make sure that things don't get lost in translation, which for many of my colleagues who were nervous of talking to the media is one of the big fears, that you say the sky is blue and the article comes out and says, scientist says the sun is exploding. Because you get the message changed here, the scientists control the message. And you work with an editor who doesn't change what you're saying, but helps you write in a manner that is approachable for a general audience. So I really love this website and like to recommend it.
Yeah, I wish the conversation had been around when I was doing the media for Markarian 1018, which you can imagine went some interesting directions, because as soon as you started saying binary black hole system, we got some very, very interesting articles that came out.
Yeah, you always have this occasionally. Fortunately, I've got a fairly thick skin to it, but the one that I always remember is I talk in a fairly unguarded fashion with people, and it led to one news article coming out of Perth that talked about astronomer lambasts and Murdoch media. Because I made there were some comments about an article that had appeared in a British newspaper called The Sun, and I happen to support a certain football team. So I just said after it, yeah, of course, this research was rubbish, this story was clearly rubbish because I saw it being published in The Sun. And suddenly that became the headline. And I stand by those comments wholeheartedly. Do we have any more questions in the room? We've got one on the right-hand side at the back there.
This might be a silly question, but where do black holes go after they suck everything in?
That's not a silly question at all. Nowhere. Because essentially, a black hole, it just grows and grows and grows and grows, right? Unless, as you say, it has sucked everything in. And if there's no matter left anywhere near it, then, and it's left alone for billions and trillions of years, they actually evaporate, which sounds really weird. This is called Hawking radiation. And it's very complicated, but kind of, to put it simply, it's to do with information transfer. And essentially, numerical information is leaking from these systems over trillions of years or billions. It takes a really, really long time for a black hole to evaporate, but it does happen. So if we had a black hole and then we left it alone in a box by itself, yeah, it would evaporate.
The smaller the black hole, the quicker it happens.
Yeah.
So this is back when I was in my early teenage years. There was a book that came out which caused an utter sensation because it became a huge bestseller despite having equations in. And that was A Brief History of Time, which was Stephen Hawking's.
Yeah, which was a fabulous book.
And that's what that's all about, or at least some of it is what that's all about.
Yeah, so I mean, if that's interesting to you, then perhaps look up A Brief History of Time on Wikipedia. Maybe a bit much to read the whole book, but you know.
I think I read it when I was about 13, and I would not want to read it now.
Did too. But I think that just tells you something about why we ended up where we are.
We've got the question here.
How do the stars get pulled into the black hole if they're already orbiting it?
That's a really good question. So that's what I was saying. When you have an interaction happen, it disrupts everything's orbits. So that's how you can start to get things disrupted from their orbit and falling in. Alternatively, stars don't always exist in single systems like the sun. In fact, don't we say like 3 out of 2 stars are binary? So most stars exist in binary and up systems. So this means that the orbits are perhaps less stable. And so if you have multi-star systems, they don't always last for the entire lifetime of a star. And so they can get chucked out. And so you can end up with these stars that are just floating around galaxies. They're called hypervelocity stars. And eventually they will, assuming they live long enough, move towards the center of the system where they might fall in. Alternatively, you can just have, so in the center of galaxies, there's a bulge of stars, which is kind of that bright spot of light that you might have seen. And within the bulge, the stars are much closer than they are out here in the sticks, right? It's like being in an apartment versus being in your nice house in Toowoomba. All these stars are whizzing around very, very close to each other. So it's quite easy for some of them to fall off their predefined orbits and end up in the black hole.
I mean, there's a natural extension to that. You saw the wonderful video that got the Nobel Prize of the stars moving around the middle of the galaxy. Those stars are not all aligned with one another. So if they're all whizzing around and they're swinging close to that black hole, they will encounter each other. And that means that they can throw one another around, which led to kind of, I guess it's MC's privilege of asking a question. Has anybody yet done any dynamical modeling looking at those stars, because we now know their orbits fairly well, to see whether they're going to disrupt each other such that we're going to get another active galactic phase with one of those stars getting chucked into the black hole and nommed in the near future?
I mean, I'm sure somebody's looking at this. I always wonder this about simulations, is why don't we project them into the future? We only ever model up to the present
That's all
day.
I ever do in the solar system.
Yeah, I know. And I'm always like, why don't we project into the future? Anyway, but that's more of a philosophical question. I'm sure somebody is. I think the problem with orbital dynamics is, as you well know, it is very unstable. And small perturbations will cause large things in the future. And so I would suspect that 40 years of data you would think would give you some pretty good constraints. So, I mean, maybe I don't pay much attention to galactic stuff. So I would have to ask, I'd have to phone a friend probably.
We'll take that one on notice then. Do we have any more questions in the room? Another one up at the back there.
Hi, this is actually an astronomy question. When we merge with Andromeda, will we see an end to all of the celestial formations that we've known, and will we finally be free from astronomy?
Astrology.
Astrology. Oh my goodness, I'm so sorry.
At least you've muddled it in the right direction. If you muddle it in the other direction, the astronomers get upset. Probably there will be some changes. So the thing I didn't mention is that, so it essentially would depend upon how, okay, the first thing to say is that the constellations do not look the way they looked when star signs were defined in the first place. So they've already changed. And so yes, on this timescale, even without the Andromeda Galaxy appearing, they will have changed by then anyway, just because of the motions within our galaxy. So yes, they will change. And I'm sure somebody will come up with a new system. But I guess that's kind of the answer. It will change, yes, but it's already changed sufficiently that I think like if you actually look, some of them don't line up anymore properly. So I think
yes. So what I'm just going to screen share this. There's an amateur astronomer called Tony Dunn who has built a fabulous online tool, which is this proper motion simulator. What you're seeing here at the top left is a clock running forward. And I'm actually going to log back a bit to, don't want to go that far. Really don't want to go that far. We're now 33,000 years BC. So this is within the scope of traditional knowledge here in Australia.
I'll look at it too.
Yep, I'll dim the lights here and I can rewind it again. There we go. So what you're seeing overlaid on this, that point that's twirling around here is the direction of the South Pole in the sky. That's the precession of the Earth wobbling. This is Alpha Centauri, the nearest star system, along with Proxima, the nearest star, moving over tens of thousands of years. You see how fast they're moving through the sky. I'll just rewind back again. We're now 85,000 years BC. So the more distant a star is, the less it moves from year to year across the sky, even though it's still moving very, very quickly. So the things that are whizzing across here really fast are the nearby stars. And Alpha Centauri, I think, is still to enter stage top of the screen.
Yeah.
What this means is that the constellations are very transient. They are asterisms, they're just pretty patterns in the sky made by bright stars that are not that far away. And even on timescales of human knowledge, the constellations have distorted and moved. Now, the website for this, he's got a number of other simulations, and you can just point where you want to and run the clock forward and backward. The further you go, the less accurate it gets. So if I ran this forward to 3 million years in the future, most of the stars start to bunch up on one side of the sky. And that's because all the bright stars are actually moving at a slightly different speed to the sun. The sun's a slightly older star. So all the things that are currently bright to us are going to rush off in one direction. And we don't really know what will be bright that's going to come in to replace them. So it's quite cool.
That is very cool. It's quite trippy as well, actually. Don't stare at that for too long.
Get a little bit busy as time goes on.
But yeah, I guess astrology is a bunch of nonsense, unfortunately. So my joke was actually a bit silly at the beginning. I don't actually believe in astrology. But I guess the interesting thing to think about when mergers happen is kind of independent of this. Galaxies are mostly empty space. And so people often ask me what will happen to the Earth. And the answer is probably, well, I mean, it'll be swallowed by the sun, maybe. But the solar system probably wouldn't be impacted as a unit, right? Because most of galaxies is actually empty space. And so it's quite a low probability event that two things actually collide. Even in a merger of two galaxies, it's mostly a global effect rather than things happening on a local scale.
I think that's possibly a good time to finish the questions and let Rebecca have a drink and a bit of a relax. So let's thank Rebecca once again. Thank you. So what we're going to do for this next bit, my colleague Duncan is going to start screen sharing in a second. He's currently up at the top. He was here at the very start. He was the person who said goodbye to the wonderful musicians and then ran away. And the reason he ran away was he's driven off to our observatory. That's about a 40-minute drive away, which is why it's really good that Rebecca talked to us as long as she did and we had so many questions. So it's let him get into the observatory and get set up to give you a bit of a show. And I think Rebecca's actually probably going to now go and do the same drive. And you're going to go try and see if you can see your galaxy, aren't you? Our email addresses are all on the website as well. Many ways to get in touch. So yeah, thank you very much. I'll let you, Duncan, take the floor with the microphone and just yell when you want me to get involved, basically.
At the moment, I'm sharing images of Saturn that we're taking. What you can see is the night sky is a little bit jittery at the moment. We've got what we call pretty average seeing. It's not a very calm sky. So the exposures of Saturn are showing up a little bit blurry and jumping around. That exposure is, what are we seeing? 5,000, some random number, 5,391 microseconds. It's about 5 milliseconds. That's because we're using a telescope. I've got an image of it up in the background here somewhere. We're using a telescope that we call Raptor, this one here. And this is the telescope we're using, and it is pretty big, an 80 centimeter diameter primary mirror. And as a result of that, Saturn is pretty bright in that context. So that's why we have such a short exposure. I'll just flick back to that.
Can I just ask a question, Duncan? Sorry to interrupt, but we've just had a message. We as our staff have a Discord server that we use to communicate with each other, which is why my phone just beeped. Shashir, who gave the talk last night, for those of you who are here, has just been outside with his phone, and we have the aurora visible right now. It may not be something you can pick up with the unaided eye, but he's got a photo literally with his phone pointing to the south. Unfortunately, as you can tell, the moon's really bright there.
Yes.
But I wanted to let people know, because getting the aurora visible from our latitude is quite rare and quite unusual. So we've got an auroral storm going on at the minute. What that means is if there are some of you that want to try and find somewhere to look due south and have a go, we'll not be offended if people duck in and duck out. So feel free to head out, try and find somewhere you can look to the south, come back in. We'll still be here, we'll still be talking. Duncan, any hints of it on the all sky camera there?
So this is the all sky. I ran this 2-minute exposure a little while ago. This is a color camera. As you can see, it gets very dominated by the moon, which is straight up at the moment. In this image, the south is to the right-hand side. This is where we should be seeing the aurora. I can't see any obvious effects, but just mostly because it's so contaminated by the moon.
Do you have the ability to open the Discord window in Chrome there and pull up the image Shashir just shared? It's in the off-topic chat. It's looking south, and it's very obvious red from his mobile. So this really is flying by the seats of your pants stuff, folks. This was not planned, but is sufficiently awesome. I wanted to totally derail Duncan the minute he started.
That's all right. So it's an off-topic. I see it here. Oh, wow. That's very nice. I'll definitely show that. Okay. Share my screen again. Zoom, zoom, zoom. That the image you're after, Jonty, I think?
Yep.
So this is from Shashir, one of our speakers, as Jonty said last night, taken with his phone. That is pretty impressive with a phone. I'm not sure what sort of exposure time he can get, but that looks excellent. My all sky, unfortunately, see what Shashir is able to do is remove the moon out of the camera frame, and therefore it's able to get better contrast. Whereas the all sky, I can make it run a long exposure, but I'm reasonably confident the moon is just going to stretch its brightness so that we won't be able to see much. We might get a red tinge, but I can certainly set that running while we go back to Saturn and start imaging some clusters and galaxies. I think since we've had a galaxy talk this evening, we should probably start with a galaxy or two. But that's a really nice photo. So if it looks that good with just a second or so of cell phone, then it may well be nicely visible by eye. As you can also see in this image, it's not so obvious in the all sky. We do have some clouds in the sky, so I might end up slewing to an object and it turned out there's a cloud right there. But the conditions are not too bad, so we should be able to do a little bit of viewing. So I'll scooch that to the side and go back to our images. This was the all sky. Maybe I'll set it on a 10-minute exposure and we'll see what comes out of that. I suspect it'll be moon saturated, but we'll give it a try.
Yes.
So going back to our ASA telescope, we've got a number of telescopes here on site. There are around about 10 or so, but maybe I'll just jump to a Google map showing you where I am right now so that you have a reasonably good idea. In this Zoom, in this Google, it also shows you where I live, my house. It's not too far from Toowoomba, but if I go, what are we talking? Mount Kent Observatory, then it'll flag in. This is our observatory here. Now I'll just zoom out for some context. So, I mean, you all know where you are there in Toowoomba, but we're on the east coast here of Australia and just about 40 minutes drive south of Toowoomba. And in here, Google's got a nice image, pretty up-to-date image of the observatory. I'm in this building here. And we're using the telescope that's in this dome here. It's our largest telescope on site. Almost all of these domes have 0.7 meter diameter primary mirror telescopes in them. This one we're using in this particular dome is a 0.8 meter, gets a little bit more light. But these are pretty large telescopes. They're small on the scale of professional size telescopes. They go all the way up to 10 meters here on Earth. And as probably was mentioned there, JWST, which is about a 7.5 meter telescope in space. But this is a 0.8 meter telescope, and we're going to use that to do some live imaging of galaxies soon. So this is our control computer. This is where we'll be able to switch between imaging planets and galaxies. It's a little bit of a switch because it's a very different scale of brightness. But what I thought we would do is just briefly try and get this Saturn image. So Saturn is up at the moment. I know I get regular messages from Google on my Google feed telling me that Saturn's rings are going to disappear and things like that. This is a fairly common media thing where I think it's somewhat misleading. Jonty was mentioning earlier about controlling the messaging. If you see that and you're wondering what's happened to Saturn and how on earth does it get rid of its rings, all they're really talking about is if you look at Saturn here, you can see the rings are pretty close to edge on. When they're exactly edge on, then we can't really see them because they're extremely thin. So when they say the rings are disappearing, they really just mean we're going to move into a position relative to Saturn where its rings appear directly edge on, and so we won't be able to see the rings anymore. But at the moment, you can see the rings have a little bit of a shape to them. It's a little bit blurry there, but
yeah, the whole reason behind that is that Saturn's tilted over on its axis similarly to the Earth by about 23 degrees. So as it moves around the sun and as we move around the sun, twice per Saturn orbit, we pass through the plane of those rings. Some of the time we're above the plane, some of the time we're below. So in a quarter of a Saturn orbit from now, the rings will be pretty much as face on as you can get them and they'll be brilliant again. Then we'll have all this similar media drama again in about 13 years, 14 years, when the rings are disappearing. And it happens all the time. It's a bit like the supermoon. We get called up for these things and people get ever so energized and excited.
Now, I'm just going to switch to one of the objects we looked at the other night. Maybe I'll start with maybe a star-forming region, the Omega Nebula. Can you talk a little bit about a star-forming regions, Jonty, while
Yes.
I go to that spot?
So basically, in Rebecca's talk, you saw pictures of galaxies that were far away, and you had those star-forming regions that were the pink blobs, essentially. Now, if you looked at our galaxy face on, you'd see the middle's a bit yellowish, but the spiral arms are mainly blue with dark bands through them. And the blue arms are because you've got young stars, and the brightest stars when stars are young are the blue stars, so you get a lot of blue light. But you'd also have dust bands and pinkish glowing clouds. The galaxy is littered with clouds of gas and dust all over the place. And initially, they're just dark because they block the light from anything behind them, so they look dark like a cloud in front of a light source. But something can nudge them and cause that gas and dust to start collapsing under gravity, and eventually form stars in the middle of that cloud of gas and dust. Those stars turn on, throw out radiation, throw out stellar winds, throw out mass ejections like what's causing the aurora right now. And the combination of their radiation and those winds will blow the gas and dust away until eventually they blow a hole in the side of the cloud and we can see into where they're forming. At that point, the gas around them that's left is mainly hydrogen because most of the universe is mainly hydrogen. But the radiation from these stars excites that hydrogen, and the hydrogen re-emits it at very specific wavelengths. Again, just like Rebecca was talking about earlier on, one of those wavelengths is called hydrogen alpha, and it's in the red, it's at about 656 nanometers. And that's what gives these star-forming regions their beautiful pink glow. So when you see an object like Duncan's imaging here, just starting to come into view, you're seeing an area where young stars have recently been born. The radiation from those stars has blown away the gas to the extent that we can now see them. They are exciting that gas, causing it to glow. And if this were a color image, all that beautiful wispy white glowy stuff would be beautiful pink glowy stuff. So I'll pass back to Duncan now, because that's enough waffle, and he can tell you how the imaging's working.
Yes. So what we're doing here is, as Jonty was saying, this is a black and white or a monochrome image. That's because a lot of the science that we do with this telescope is measuring the brightness of stars. And for that purpose, we want to have every pixel in the maximum area of that pixel sensitively measuring the flux or the light coming from whatever objects we're looking at. In this case, that means you get a monochrome image. You're just measuring the brightness for the sensitivity over a number of colors. This is an optical camera, so it's essentially sensitive to all the way from blue and a little bit into the UV, all the way through to red and a bit beyond that into a little bit of the infrared. That's a typical optical camera sensitivity. When you see color cameras, actually I have a few around here. This, I should show, is actually the camera that we're using on the telescope. It's a pretty large frame camera. I'm not sure if you can see. There's not a lot of light. Maybe I can turn the light on behind here to give me a little bit better image. You can see there's a pretty large frame camera.
So Duncan, we can only see your Google window at the minute, so we can't see your video of you.
Yes, I will just stop my screen while that image continues to accumulate. I'll talk about that in a moment. Stop my share and you'll see me. This was what I was trying to show you. This is it looks gigantic when I hold it very close, but you can see it's about sort of, half the length of my finger. This is a relatively large frame detector. So there's a lot of pixels involved here, but they're all monochrome. If we want a color image, the way we do that is every group of 4 pixels, a little square of 4 pixels, is actually assigned an individual color. We put a little filter over them. It's called a Bayer matrix filter, and it assigns a color to each individual pixel. And then what you're really looking at is 4 pixels combined into one, where each pixel was assigned a color: blue, 2 greens, and a red. And then those pixels are all combined together to give you your color. And indeed, if you zoomed in on the monitors, computer monitors like the one I'm looking at here, they're also made up of pixels that are made up of 3 stripes, blue, red, and green, in order to project the colors. So that's how we would normally produce a color image. There are a few different ways that I'll talk about a little bit later when we show some images, some astrophotography that Jonty, myself, and a couple of expert astrophotographers took recently. But for now, what we're doing, I'll go back to sharing my screen, is these monochrome images. Now, I talked about they're stacking up, or they're combining their images. I've got an exposure time here of about 10 seconds. I'll make this just a little bit bigger so you can see it a little bit better. I've got an exposure time of 10 seconds, and we're actually adding those together. So we are, I zoomed in a bit too far, sorry. I think if I click that one, it will auto-fit it. So we can add those images together, and as it adds them together, the details get clearer and clearer. Last week when we were doing this, Jonty was giving a talk in Springfield. I was able to do about a 1-hour stack whilst he was giving his presentation, and this time I haven't been out here long enough to be able to do that. But you can see in just a few seconds, even a minute or so of stacking the images up, and you get a pretty clear picture. The picture of the gas, the dust, and the stars, as well as the dust creating these darker regions. Unfortunately, you can't really see my mouse. It ends up being a tiny dot on the screen, so I can't easily indicate things to you, but I think Jonty did a good job introducing things there. So these are the kinds of images we can get in just a few seconds, but they're also the kinds of images you can get with small telescopes and camera systems as well, if they're set up to do so and you've got a nice sky.
Yeah. You also have at the bottom left there, this window tells you a lot about what's going on. So at the minute, we've just hit the 25th image stacked together, giving us a total exposure here of 250 seconds. So if you're watching at the bottom, it's actually telling you what's happening as the images are taken.
Indeed. Now, I thought what might be good, because I think we'll catch it before it heads off, is we'll have a look at a couple of star clusters, and then we'll go to some galaxies to make sure that we get a couple of images of galaxies, since this was a galactic focus talk today. So maybe
Yes, can also, I was going to say, we can also try and get either the dumbbell or the helix at some point.
Yes, I've got the helix on the list here to go
Sweet.
to soon. So for now, I'll just go to the Pegasus cluster, so a globular cluster. Jonty, if you can talk about that for a moment, I'll zoom over.
So there are two real types of star clusters when we categorize them. You can break them into finer and finer groups, but star clusters are groups of stars within a galaxy. It's a smaller unit of measurement. So I guess it's like a class rather than a school, if you kind of get the idea. It's a group of something together. A globular cluster is quite an unusual thing. There are hundreds of them rather than millions of them in a given galaxy, and they seem to date back to right when the galaxy was forming, when it was young. For a galaxy like the Milky Way, which is essentially like two fried eggs slapped back to back, so most of the materials in the disk of those two fried eggs, the globular clusters are scattered all around it in a much more spherical halo. And they are huge agglomerations of very old stars. When I say huge, you're talking about an area only maybe 100 light years across. So light would take 100 years to reach from side to side. That's big compared to the Earth, but small compared to the galaxy. In that region, you've got millions of stars, all gathered together under their own gravity, all orbiting around their own common center of gravity. At the middle, there's probably something we call an intermediate mass black hole, which is intermediate between the small black holes that, well, I say small, the black holes that stars make when they die, the supermassive black holes in the middle of galaxies. Intermediate mass black holes are in the middle. Yeah, again, astronomers are very innovative when it comes to naming. So what you're seeing here is one such globular cluster. The density of stars is highest towards the middle and falls off as you move outwards. But this density of stars you're seeing in this cluster here is incredibly vastly more than we have in our local environment. So the nearest star system to the solar system is Alpha Centauri and Proxima Centauri. They're going around each other. They are 4.2 light years away. In this cluster, if we were in the middle here, there will be hundreds, if not thousands, of stars closer than that to the solar system. So you'd step out in the night sky and the sky would be scattered, bedazzled with stars. But we've never found a planet in one of these clusters. And part of that is that the stars are so close together that they're continually interacting, coming very near each other. So the explanation people have got for why we've never found a planetary system in these clusters is simply that the stars are so tightly packed that any planets that could form would be stripped away from their stars fairly quickly. But also that the stars form so close together that the planets probably never got to form in the first place. These are ancient. They date back to the formation of the galaxy, so they look unusual, but there are so many stars that are so close together, they are very robust against being pulled apart, which is why they've lived so long. So I'll hand back to you, Duncan, there to say a little bit more about exactly what we're seeing here.
No, I think you covered it very well, but essentially what we're looking at here, the one thing I was going to mention is just that these stars are old. When we measure the age of this, we really are talking the beginning of the galaxy. These stars are often considered our second generation stars, where the sun would probably be considered a third generation. And there's possibly, because I missed the lecture, I'm not sure exactly what was covered, but maybe there was some early universe JWST stuff mentioned in Rebecca's talk. But some of the exciting discoveries that have come out of recent work with looking at the earliest universe in the first billion years of the universe being 13.7 billion years, was that stars as early as 400,000 years into the age of the universe were already showing heavy metals. Did Was that covered already? Maybe I'm repeating.
No.
It
No,
wasn't.
Rebecca focused on the galaxies going smush into one another, so she was all about collisions.
Of course, and that is her research focus, so that's perfectly fine. So one of the things that that JWST has, it's an opportunity for me to give part of the talk I didn't get to give yesterday. One of the things that JWST has discovered is that even some of the earliest stars we can observe, looking back to when the universe was less than 1 billion years old, its early universe, the stars already had metals in them. And this is a confusing situation for us because the way metals are, and elements essentially heavier than about oxygen or nitrogen, the way they're generated is primarily through a supernova. Now, in order for the stars in that 400,000-year-old universe to have metals in them when they haven't themselves gone supernova means that there needs to be a previous generation of stars. Now, that previous generation, that first generation of stars, from all of our understanding, should have been made up almost completely of helium to about 75%, and hydrogen to about 75% of it, and helium about 25% of it, and then maybe the most minuscule amount of lithium and nothing else. So out of that first generation of stars that must have lived and died by the first few 100,000 years of the universe, that's an incredibly short lifetime for a star. Then we have the next generation, the second generation of stars, including the stars that we are seeing here in this globular cluster. Now, that's confusing for us because there's a number of issues with creating a hydrogen-helium star, because a lot of the way stars form, they need to condense down. And in order to condense down, they need to give off a lot of their heat because they're moving around. It's the early universe. There's a lot of radiation, a lot of heat. And so in order to radiate away that heat, you need a lot of electron energy levels and things like that in your atoms. That typically is done through heavier elements. They didn't exist at that time of the first generation of stars. So how could they have formed early? This is one of the big arguments for dark matter, as opposed to, for example, modified gravity as a solution for understanding what makes up most of the mass in the universe. As that dark matter was actually forcing the rapid formation of those early stars. That's something we're finding out about now, the last couple of years, and JWST's work has been amazing for that area of science. It's not my specialty, but I do think it's a fascinating subject.
Yeah, there's a lot of this is, I was going to say, this is really indicative of how little we know. So there's a famous quote, which I'm probably going to butcher, from a patent clerk in 1899, who essentially said, everything that will be discovered has been discovered. We are the pinnacle of knowledge. Basically, when we look out into the universe, we're playing detective and we're trying to answer the questions we don't know the answers to yet. And I think the reality is that we are at the beginning of a journey rather than the end. There's a lot more to uncover. Just to give a bit of a language translation here. Astronomers not only have very innovative naming systems, but we also tend to simplify everything we can as much as possible. So when Duncan's talking about metals, he isn't just talking about iron and nickel. He's talking about anything that isn't hydrogen and helium, because to astronomers, the periodic table is hydrogen and helium and metals. So we're a bit weird like that. So it's one of those things where language is contextual and the words we say mean one thing to us and a different thing to the person listening. So I wanted to clear that up, that when we're talking about metals, it's anything that isn't hydrogen and helium. In other words, pretty much other than lithium, anything that is made by stars rather than pre-existed in the universe. Just a clarification. Anyway, back to you, Duncan.
There's one other thing I wanted to cover in this image before I go to the next object. It's just this star. I'm not sure if you can see my mouse. Maybe you can. This star over here on the left, you can see it's nice and bright, brighter than most of the other stars because it's not part of the globular cluster. It's in the foreground. And it has a sort of cross here. This cross that you can see, and you'll see that a more interesting shape if you look at some of the JWST images and things like that. But if you see Hubble, it also has crosses in its star. It's actually what we call diffraction spikes. I'm going to just stop sharing to show my room here for a moment and zoom in on what we've got just over here is what we call the truss part of one of our larger telescopes, 0.7 meter telescope. Its primary mirror is getting re-illuminized at the moment. And I'm just going to bend it over for you so you can see why you might get that cross. This is the secondary mirror. I'm not sure if you can see it that well. Maybe I can a little bit closer. It's not too heavy, but it's also not too light. This cross part, this secondary mirror, weighs about 15 kilograms or so. It's suspended by thin aluminium pieces of metal that holds the mirror in place very carefully. That cross actually comes through in the images, meaning that any point source will show up with that cross. The main reason you could see it very clearly with the particular image that I was sharing, which I will share again, is because that's a particularly bright star. Any star that was bright enough would show this kind of cross effect, these diffraction spikes, but it's most obvious in that one. You'll see the same thing, as I said, in space telescope images and others that have a secondary mirror or a mirror system. JWST has a number of mirrors that make up its system, so it has a very interesting diffraction spike set in its images. So just to explain what they are, as opposed to with a number of images, and we'll see this with the galaxy we're going to look at soon, the resolved objects, the objects that actually look like a shape as opposed to just a point, those resolved objects don't show diffraction spikes. So you don't see spikes around a galaxy, for example, because you've resolved that as an object. Whereas all of these point sources of stars are so far away, despite the fact that they might be quite large objects, that they appear as a single point of a light source.
Yeah, there was actually a new James Webb Space Telescope image came out this week, which has had people wowed, which has those diffraction spikes on to an incredible extent. Now, one thing that has sparked is a lot of discussion from people, because a lot of people went, that's what I see when I'm driving at night. And then other people went, well, I don't see that. It turns out that if you've got an astigmatism, you get similar kind of spikes and streaks coming out of oncoming car headlights. And the worse your astigmatism, even if otherwise your eyesight is very good, the worse that can get and the more difficult you can find it driving at night. Now, I'd never realized this because I'm a glasses wearer and I get this a bit, until a friend of mine in the UK was talking about the fact she'd always struggled with night driving, had a terrible time. And then she got her first ever pair of glasses that corrected her astigmatism. And suddenly that problem disappeared. So you see similar things. And what's been interesting to me is not just this James Webb Telescope thing being really spectacular. It's a way that sometimes when we're talking about these things, connections are made that we don't think of that help to educate people. And who would have ever thought that an image from JWST could encourage people to go to the eye doctor to get glasses to improve their safety driving at night? Yet that's one of the results that image is going to have. It's absolutely astonishing to me. And yeah, why do we do astronomy? Sometimes it helps improve people's eyesight. Anyway, Duncan, over to you again.
Okay, I'm just going to go to the Helix Nebula. I think I've just made the move there. So maybe you can give a brief introduction about planetary nebula, and then I would like input as to which galaxy to see. I think Des had a good input last time, and I didn't write it down. I've got a little list of things to observe, but I don't have a good galaxy other than NGC 253, which is a bit challenging to find. So
there's a few. We had them. We will do. I'll get Des to think about it. I know when we had our astrophotographers here, we had the meetup, which came out quite well as well. But I'll let Des, so Des at the front, who's been running the webinar, is one of our unsung heroes here and has been doing a lot of work. If you've had communications with the uni about the festival, you've probably talked to Des. He's also a very, very important part of Queensland's amateur astronomy community and knows the night sky very, very intimately. So he's a really good resource for what should we look at next. But what we're looking at next right now, which will gradually appear on the screen as I waffle, is something called the Helix Nebula. Now, this is not the kind of nebula we looked at before, where stars are being born. This is the kind of nebula that is formed when a star dies. For a star like our sun, when it comes to the end of its life, it'll swell up to become a red giant. And that's why earlier in the talk, Rebecca mentioned that the Earth might one day be devoured, maybe in about 7 billion years' time. That's under debate because we don't know whether it will quite reach us and eat us or whether it will just bake the Earth in a horrible way but leave us intact. But once the star passes through this red giant phase, it will eventually shed most of its outer atmosphere, blowing it off into space in something that is less violent than a supernova, which is when a star detonates and explodes. That's a much more massive star than the sun. This is a gentler process when observed from a distance, but it probably wouldn't be gentle from the point of view of planets in the system. You've got an entire star's worth of atmosphere being flung off into space. and it leaves behind the core. An object the size of the Earth, but a mass similar to or smaller than our sun. Tiny little speck that is no longer burning with the fires of nuclear fusion. It's just super hot and it cools down over billions of years. Starts ultra blue and gradually fades through blue and white and eventually will go yellow and red and fade out. All that gas that is ejected expands out into space and is illuminated by the ultraviolet radiation bouncing outwards from that leftover exposed core. Gets bigger and bigger as time goes on. So as this image gradually comes into view, as it fills in, what you're going to see is essentially a celestial smoke ring, an incredibly beautiful gaseous diaphanous vision in the sky that is the atmosphere of a star that was once like the sun, that has reached the end of its life and blown off its outer atmosphere into space. This ring feature that's coming into view here is that atmosphere that's been shed, and as time goes on, as we get more images, this will get clearer. It's not quite as clear as it was last Friday because the moonlight's making it a bit harder to bring out. But this is one of the most famous, one of the most spectacular planetary nebula in the night sky. And these are temporary transient objects. They're only visible like this for a few tens of thousands of years. For that period where the gas is far enough from the star to be big enough in the sky for us to see, but near enough to the star and still dense enough to be lit up brightly to glow. This thing will just gradually get bigger and bigger and bigger and fade to black over time. This one, the helix, has been imaged from James Webb, from Hubble. It's the kind of thing when you get a really good photo that kids who are mad about astronomy like I was, this would be the kind of thing you get as a poster to put on your wall. It's really, really spectacular. And it is essentially the shroud around the corpse of a dead star that was once like the sun. And I'll pass back to you there, Duncan, because it's slowly dropping into focus.
Yes, sorry, it's taking a while. I think exactly what you're saying. We're lacking a little bit of contrast here to bring up the shape. I might just jump across to what I think I have prepared is
here's one we made earlier.
Yes, here's one we made earlier, exactly that, in multiple colors.
I'm guessing the ring is probably a little bit too low at the minute for you to get to it. I mean, it never gets that high, but that's a smaller one on the sky and therefore has a higher surface brightness. You've got the same amount of light spread over a smaller area, so the individual bits look a bit brighter. It's a perverse thing. You can have something that's bright but's made out and so therefore is less obvious.
Yes, indeed. So maybe we've been going for a little while, so maybe I'll jump to a galaxy in a moment, but I'll just briefly introduce this. So we did do some astrophotography a few weeks ago here from the site. This was an image taken with the
So we're still seeing your imaging camera, by the way.
Oh, am I not sharing?
I think you've not tabbed over. So we're seeing your mouse at the minute moving around. We're still seeing the image, although it's not.
Oh, I see. Yes. I will just share my whole desktop.
Shared the window, not the screen. There we go.
Okay. So
that really is one we made earlier.
Yeah, one we made earlier. This one was taken a bit of a special way. Rather than just using a color camera, something you might be familiar with, like a DSLR camera, we actually used little filters, little square filters that say, I'm going to let through blue light of a very particular wavelength that corresponds to light we know the nebula is emitting. So in this particular case, I think it was, in fact, if I go to the next screen, we've got a little bit of information about that. It was an H alpha, so that's that hydrogen alpha that Jonty was talking about earlier, and oxygen, particular wavelengths that those two atoms in this nebula are emitting light at. And so we're able to isolate the fact that the oxygen is closer to the center here, and so the blue color sits more in the center, and that the hydrogen is a bit further around the outside, emitting that red color. And we combine those, we assign the hydrogen image that we got, which shows the intensity of the light from hydrogen, to a red color. We assign the intensity of light distribution we got in our image from oxygen to a blue color, and then we combine the images together to get something like this, which I think looks remarkably like an eye. But as Jonty said, this is caused by that star right in the very center. That star is the one that has puffed off all these outer layers. So if I go back to our image, we're not quite getting the contrast that we were getting, and that's just because of our bright moon. So maybe I'll try and jump into a galaxy now. So I'm pretty sure we've got a spiral galaxy that I will try to go to. So Jonty, can you talk a little bit, if it wasn't already covered, about spiral galaxies?
Sure. So Rebecca talked mainly about spiral galaxies, in fact, but there are galaxies of all types. You've got little galaxies that we call dwarf galaxies, and then the galaxies that are kind of grown-up adult-sized galaxies. In other words, the ones that were easily visible to telescopes 50 or 100 years ago, when people looked through the eyepiece or took photos with photographic plates, have a variety of shapes. So people looked at them and categorized them by their shapes primarily. And they even made something famous called the tuning fork diagram, where they tried to link the shapes together into a story, a narrative of galaxy lifetimes. When the Milky Way and Andromeda Galaxy have collided and all the gas has gone and you're left with a blobby thing that looks fairly yellowish, that's an elliptical galaxy. But something like the Milky Way is today, something like the Andromeda Galaxy is a spiral galaxy. And from side on, spiral galaxies look pretty much like two fried eggs slapped back to back. You get a yellowish bulgy bit in the middle and then a bluish extended disc tapering off in both directions. When you look at them face on, that yellow blobby bit is still at the middle, but coming out from it are curved spiral arms. So this is the Sculptor Galaxy, I think, 253. And what you're seeing is the glowy yellow blobby bit in the middle is clearer because that's a brighter bit. And you've got the disc. This isn't quite edge on, but it's nearer to edge on than face on. That's the angle you're looking. So imagine you've made one of your fried eggs and it's sat on your plate and you're looking at it from a fairly shallow angle here. That's kind of what you're seeing. But the dark bits you're seeing here are real. These are the dust bands that are part of the spiral arms. That's the gas and dust that is blocking out light from things behind it that a long time in the future will go on to make the next generations of stars. This is the equivalent of when we don't have the moon in the sky and you look at the Milky Way, you see the dark bands through the Milky Way, you see dark clouds like the Coalsack Nebula next to the Southern Cross, which forms the head of the emu to the traditional owners of the land. We have these dust bands in our galaxy. When you look at spiral galaxies from outside, you do see these dark bands as well, lacing the spiral arms as locations where stars will be born in the future. So your screen's just gone to the start stacking screen there, Duncan.
Yes, that's because the first image was not being stacked with, so I've just increased the exposure time a little, so it should stack a bit better. So do you have an image now?
Yeah, we have an image now, and we've got quite a bit of detail. So the points of light dotted around across this are foreground stars. They're things in our galaxy. The galaxy itself is in the background here. Now, if you zoom in enough, you may have seen like the James Webb Space Telescope did a deep field. The Hubble Space Telescope did a deep field as well. And Duncan talked about these a little bit last night. If you were to zoom in, not on the middle of this galaxy, but say on the top left part of this image, where there aren't any stars, pick an area there, zoom in and take a really long exposure, you might see a couple of stars in our galaxy, but you would see hundreds, thousands of galaxies. There are more galaxies in the night sky than there are grains of sand on the planet Earth. Most of them are too fancy, even with the telescopes we've got here. But the bizarre thing about the universe is the more you zoom in with, the bigger the telescope you get to a point where you're not seeing stars in our galaxy anymore because there's only 400 billion of those, which means that the night sky isn't entirely packed with them. There's a lot of gaps. When you look in the gaps are full of galaxies. This just happens to be one that's very nearby and therefore big and spread out on the sky. And is now coming in beautifully, so you can see the dust bands and the arms a little bit more clearly. Back to you, Duncan.
Excellent. I think that covers probably this galaxy. I'll let it run for another couple of stacks. It's doing 30-second stacks here to make sure that we get enough stars that it can align the images and add them together. So as it stacks, we get a little bit more detail. I think what might be useful now is to go to an open cluster. I was going to go to the wild duck cluster after this one. And maybe, I'm not sure if the Sombrero Galaxy is visible at the moment. You might know that off the top of your head, Jonty. Is that a now object?
No, getting thumbs down from Des. That's in Virgo, which will be rising at about 6 a.m.
Okay. So not at the moment.
Other side of the sky, unfortunately. Messier 33 would be a bit too big. M31 would be way too big, unfortunately.
We do have a very large field of view, but yes, you're right. M31 is about 4 degrees. We've got about 30 arc minutes in one direction and about maybe 20 in the other direction.
Yeah. Could you lob up the all sky again? I've just had notifications from more of my colleagues. The aurora is kind of pulsing, so it's coming in and out with about a 30-minute period, and it's now got quite bright.
This was what I got from that 10-minute image I was going to try before.
Yeah.
So as I mentioned, the moon just saturates
Washes it out.
But I might go down to 2 minutes again because I felt
And just
like
have a go.
about the right effort. Maybe it should be about this bright, but it's got to retake another image. Hopefully that will give us an idea as to whether that will work out or not.
Yeah, so apparently at the moment, George, who's another of our colleagues here, is saying the aurora is very bright now. So I will totally understand if people duck out briefly and come back. A fair few people have left and are probably looking at it right now. The reason I keep bringing these updates, like I say, is the aurora is only really visible from Toowoomba once a decade on average. It was back in May, and it is again now, but it might not be for another 10 or 15 years. Easier to see through your cameras, so if you do see it with the naked eye, you'll just see that a bit of the sky is brighter than others, especially with the moonlight. It's a shame the moon is as bright as it is, because if it was new moon at the minute, this will probably be more impressive. Yeah, I can do. So question from the audience is, do I want to explain stacking? And basically what's happening is, if you imagine this picture and try and visualize it as a computer sees it, every single pixel on this picture has a number associated with it, which is how bright this pixel is. And the dark pixels have very low numbers and the bright pixels have very high numbers. And the computer then translates that into a big number is white and a low number is black, and somewhere in the middle is grayscale. Every image we take, the camera is reporting those numbers, but that's a bit noisy because sometimes it'll get a bit more light, sometimes a bit less light. So what happens is every image we take, those pixels have a certain number associated with them. And as we take more and more images, we add the numbers together and then divide by the number of images taken. So we average out what the level should be in that pixel. So this is a way of us getting rid of the noise. So what you're seeing here, we've now got many images. We've got 180 seconds worth stacked up. And you can see a lot more detail has popped out, because the areas where you've got fine differences in brightness, on a single image, those differences just get lost in the noise of how wibbly up and down it is. But when you add a lot of images together, you smooth it out and you can pick out the fine differences. It's sometimes better to do that than just leave your camera open for a really long period of time. So if you leave it open for a long period of time, the brightest things will oversaturate. So they'll fill up the bucket that they can fill and start overflowing, and then you're not getting any information about them. So it's now common practice for astrophotographers, instead of trying to take a 30-minute exposure, they'll take 10 3-minute exposures, or they'll take 100 even shorter and stack them up, and they'll get a better image as a result. Now, what that has led to is some people actually take images of things like the Milky Way without even tracking with the stars, because when you do the stacking, the software that stacks will recognize these are the stars here, align all your images together and add them up and account for the motion. So as long as your exposure is short enough that the stars don't trail, you can actually get good images without paying for expensive equipment, so long as you do the right clever things with processing afterwards. And again, I'll swing back to you there, Duncan, if you've got more to add.
Very good. I was just going to swing across to the wild duck cluster. So it's an open cluster, but I maybe would just show you briefly what I mean when I say I swing across. So I showed a picture earlier of the telescope that we are using. That telescope has a number of pieces of control software. It's an ASA, an Astrosystem Austria telescope. And so it has a focus control. It also has rotation, the ability to rotate the image. It's what we call an alt-as telescope. But it operates very similar to the telescope that's actually in the corner of the room with Jonty there, in that it's just simply 3 mirrors, a primary mirror that Jonty can maybe point to. I don't know, with the telescope there. It's a little bit Duncan, isn't it?
You are still screen sharing at the minute, so we can't see you, and we don't have. Oh no, the telescope's here. It's just hidden behind the desk.
Yes, maybe I can show you with my telescope because I've got one here as well.
That might be easier. Yeah, sure. So when we had the star forming region earlier on, the Omega Nebula, you had a group of stars that have all formed together that are clearing the gas and dust away, and they light up the nebulosity essentially. Eventually, they blow all of the gas and dust away, and they continue to move together through space with no gas and dust around them. And that's what an open cluster is. It's a group of stars that form together in space that are still moving together through our galaxy. But unlike the globular cluster, where you had like millions of stars, typically open clusters only have a few hundred, or if they're really big, a few thousand stars. And that means that they have much less holding them together against the vagaries of everything else moving around. So over time, these clusters will gradually lose members. The ones more to the edges will be nudged away and pulled off to different things. And so gradually they'll disperse through the galaxy. So what that means is that most open clusters, not all of them, but most of them, are actually relatively young. So you're seeing here, with the globular cluster, you had a really tight packed cloud of stars. Here they're more spread out. I do have a question. Really good question. So the question is, do planets form in these ones? And I think the answer would be yes. So almost all stars form as part of a cluster, as part of an open cluster. Now, you get everything from very small groups of stars forming to really big ones. There's a lot of planets have been found. We've even found planets in some clusters, particularly towards the Hyades, and we've found planets forming in star-forming regions that would form open clusters. So very different to the globulars, and that's because the stars are much more spread out. As a total aside, this ties into studies of the solar system. We have comets coming through all the time, and there's a bright comet we might be able to see next week. We can, with our observations of comets, work out all sorts of stuff. And one of the things we can measure is the amount of hydrogen versus the amount of deuterium contained within the water. Deuterium's heavy hydrogen. Perversely, when the planets were forming, the amount of deuterium trapped in water is a bit temperature dependent. So comets that formed in closer to the sun would have a lesser amount of deuterium, and ones that formed further out would have more. So if we can measure the amount of deuterium in the water, we can get a rough handle on where that comet formed. The reason that ties to clusters, you're probably thinking totally different. This is still to be tested, but I wrote a paper probably 15 years ago now, talking about this, looking into it. And one of the conclusions is that the Oort cloud, which is where the comet we can see next week comes from, is halfway to the nearest star. And that was populated by the planets as they formed. But Uranus and Neptune are less massive than Jupiter and Saturn, so they're less effective at throwing comets out into the cloud. If the sun formed in a very loose cluster, the comets Uranus and Neptune threw out would not get crabbed into the cloud and they'd fall back in. But the comets Jupiter and Saturn threw outward would get put in this Oort cloud. If the sun formed in a bigger cluster like this with more stars that was denser, the comets that Jupiter and Saturn flung out would be stripped away by those stars, but the ones Uranus and Neptune put out there would be captured into the cloud. So potentially, if we look at comets and measure the deuterium, we might be able to figure out what kind of cluster the sun formed in, as to whether there were lots of stars or whether there were very few stars. So that's one of the ways that we put the clues together, essentially, the storytelling side of science. And it might be able to tie together to figure out if the sun formed in a cluster like this, which is a fairly substantial open cluster, or whether it formed in a much smaller star-forming region. And we just don't know the answer yet. But it's a fabulous question. Okay. Yep. So I think Duncan may have just got a visitor, but this is still integrating onwards and stuff.
We'll just duck to one more object, leave it integrating, and I'll just duck away for about 4 minutes.
Yes.
What do you think is a good one? I know that I had seen 47 Tuc. It's another globular cluster,
Yes.
but one with many, many more stars. It's quite impressive.
I think 47 Tuc's probably a good one to do as our final object. Just looking, because I'm looking at the audience and most people have now left. And I think a lot of people are reaching to try and get somewhere to see if they can grab the Aurora as well. So it might be a good one to get it onto 47 Tuc. I'll talk about it a little bit and explain where it is while you let your special guest arrive. And then we might bring it to an end after that in about 10 minutes time. So he's just slewing over to this now. So 47 Tucani is the second brightest globular cluster in the night sky. It's one you can actually see with the unaided eye. Thank you, Des. It is right next to the Small Magellanic Cloud. The Small Magellanic Cloud is a dwarf irregular galaxy that was probably once a barred spiral galaxy that the Milky Way is eating. It's like a moon to our galaxy, and it's in the background. 47 Tucani is a foreground object, but it's also further away than most of the stars you see in the night sky. This is a bit perverse. So it's in the foreground compared to the background galaxy, but in the background compared to the foreground stars. Yes, that does make sense. This is what you're looking at here. It's a bigger globular cluster. We looked at the Pegasus one earlier on. This one you can tell has more stars and it looks denser. Not only is it the second brightest we can see with the naked eye, second brightest we can see in the night sky, it's also one of the more massive, one of the bigger globular clusters in our galaxy. It's not the biggest. That's another southern hemisphere object called Omega Centauri. But it's a very distinct, very visible example. If you go out and you have a wide field camera lens and you point up and you get the Magellanic Clouds, there's a bright point next to the small Magellanic Cloud that on your photo looks a bit blurry and wrong, because it's not quite looking like the background stars do. They come out really sharp. That's this cluster, and the reason it looks blurry and wrong is on your wide field shot, you can't make out the individual stars, so you've got a bigger, blobbier, more diffuse source of light there. It is a really remarkable object. It's one of the things growing up in the UK, this was on my bucket list to see when I came down and moved to the Southern Hemisphere. It is very spectacular, and like I say, once you know where to look, you can see this with the naked eye. It has comfortably more than 1 million stars in it. If you got someone like Des, each of these objects, each of these globular clusters, even though they are a shared type, a vast ball of 1 million plus stars, each one looks different. So in the same way that you learn to recognize the faces of your friends and your enemies, these images of the night sky, every cluster looks unique. When we look up and I point out the constellations on a moonless night, those patterns look unique and you memorize them. And so you can identify objects by looking. I'm not that good at globular clusters because they're not the top of my bucket list. They're not my favoritist things in the sky. But if I put this photo up in front of Des without telling him what it was, there's fairly good odds that he'd say, oh yeah, recognize that one. Yeah, and it's all down to which stars are where and how dense it is. Yes. So question here is, how big across would it be? And the number I'm going to give you here is an estimate. So it's probably accurate within about a factor of a few, because I don't know the exact numbers for this, and there's a bit of a variety, bigger ones and smaller ones. But typically this inner region would maybe be only 100 light years or a bit more across. So you get a feel for how many stars there are there. I mean, in most fields, when you're teaching, you warn people that Wikipedia is rubbish. In astronomy, it actually tends to be very good and reliable because most people who want to mess around with Wikipedia because they're being foolish don't go to astronomy articles. But also, the amateur astronomy community is very passionate about their subject. So I'm just going to bring up for the people here and Google 47 took, and I will actually be able to bring up the stats as we know them. And I can be fairly confident that what we get from Wikipedia is actually fairly accurate. So here we go. Apparent magnitude 1.4, 4.09. So here we go. So it is 15,000 light years away. 44 arc minutes across, including the extended outer regions. This is a color version of the image. Lots of information on the history and stuff like that. So yeah, radius I was a little bit over, 60 light years. Lots of information. Total mass, 700,000 times the mass of the sun in there, which, given that there are more small stars than big stars, means that there will be millions of stars in there. And its estimated age is 13 gigayears, so that's very nearly the age of the universe. Wikipedia is really good for these things. So that's a color image of the middle. That's what we're getting here now. With the moonlight, you could get better images on a properly dark night, but because this is such a bright object and it's also quite far from the moon in the sky, I think that's pretty impressive what we're getting there, and just getting better and better. That's still only 2 minutes of exposures at the minute. It's a very bright, very obvious object. I don't think Duncan's quite back yet. The interesting thing with the bigger one of these, Omega Centauri, is when you look at most globular clusters, they appear to have a single population of stars. So the thinking is all the stars formed at the same time. There's some occasional stars in it called blue stragglers that people didn't understand because blue stars are young. And the thinking is that that's where you've got two old stars that have crashed together and merged and form a more massive star that glows blue and then will die. But Omega Centauri appears to have at least two distinct different populations. And that's one of these things, again, that's a clue for us that something odd's going on. And the thinking is that Omega Centauri looks like a globular cluster now, but it's actually what's left of a galaxy that was long ago devoured by the Milky Way. Most of the stuff pulled away, and Omega Centauri is just a core of that galaxy. And so the reason you've got more than one stellar population is it formed and it evolved as a galaxy, not as a typical globular cluster. And that ties into the fact that it's significantly more massive, got a lot more material than any other globular cluster in our galaxy. So they are definitely interesting objects. Yes, I can keep filling. We've got the eyes on for Duncan there. What I may do, unfortunately, we can't control Duncan's screen there, but he will be back with us in just a moment. But I think that might be a reasonable time for us to wrap up the formal proceedings. If the aurora has started to fade out by the time you get somewhere dark, the information I'm getting from my colleagues is that it is getting brighter and fainter again with about a 30-minute period. That is not unusual. Aurorae tend to do that. And I remember you see them more where I grew up in the UK, although again, they're not that common. And you do get it waxing and waning with about this periodicity. So if it has faded down a bit by the time you get to wherever you're going and you can't see it with the camera, give it 10 or 15 minutes and have a look. Another look. Give it another 10 minutes and have a look. It might be that the storm starts to ease off, but the fact we're still seeing it from here into Toowoomba suggests we're still getting full on properly whacked. And while I really appreciate those of you who stayed with us to the bitter end here, this is an unusual enough and special enough occurrence that I would encourage you to try and take advantage of it. And even if you don't see it, you know that you were there when it happened and you did see a photo that was taken from right in our own backyard. I will thank you very much for your attention and for your company tonight. And when Duncan gets back, I'll tell him that everybody's left and he can relax. Yes. Really good question. And I'll answer that as we're wrapping up. The question is, can you see star clusters in other galaxies? The globular clusters, we definitely can do. There's more than 100 of them known for the Andromeda Galaxy. Galaxies that are further away, it's harder because they're further away, they're smaller. But the more massive the galaxy, it seems the more globular clusters it has and the more massive they are. So Andromeda's got slightly more globular clusters than we know of around our galaxy, but we think it's a slightly bigger galaxy than us. We think it's the biggest and we're the second biggest in our local cluster. Some of the really big galaxies further away likely have many, many more. But the further away you are, the harder it is to spot. In terms of open clusters, they are significantly smaller, but the most massive star-forming regions in other galaxies we can see, and tied to that we can see open clusters, particularly in our satellite galaxies. So the large and small Magellanic Clouds are really good examples. Both of them we think were once spiral galaxies that were barred spirals, and those barred spiral galaxies are being disrupted and devoured, essentially, as we go on. One of the side products of that is that all the gas and the dust in them has been smushed together and star formations happening much, much faster in the Large Magellanic Cloud than it is in the Milky Way. So the biggest star-forming region, as far as we know, actually probably in our local cluster of galaxies, is something called the Tarantula Nebula, which is in the Large Magellanic Cloud. You can see that nebula with the naked eye, despite the fact that it is in a different galaxy to us. Gives you an idea of the scale. It's so big that if the middle of that star-forming nebula was where the Orion Nebula is, we'd still be in that nebula. That's how big that star-forming region is. And it's really, really remarkable. And it even threw me. I do a bit of astrophotography, and I've never been able to get that to look right because that nebula always comes out as this weird bluish color when I'd expect the star-forming region to be pink. And apparently that is a real thing. The stars forming there are so energetic that they're exciting the hydrogen even more. And so we're not getting hydrogen alpha emission, we're getting hydrogen beta emission because the electrons are being even more excited. So the color tells you that this is a ridiculous star-forming region and the cluster that's formed in it is ridiculously big. But it's a really, really good question. On the night sky, I mean, would you say probably it's about fingernail at arm's length size of tarantula, isn't it? But that's because it's so far away. You're talking about a forming region that is about 250,000 light years away. Yeah. So Duncan, I understand you've just got back with us. I was just saying because most people have slowly left to go see the aurora. So I was thinking what we might do now is bring formal proceedings to a close and leave you to entertain Rebecca and show her the site. And we can all go and hopefully look for some aurora. So thank you very much for giving us this show tonight. Really appreciate it. And I think we need to do this more often. And there is our first speaker for the night, who's now arrived at the top of a hill far, far away. So from all of us, thank you for your company tonight, and clear skies, and hopefully get to see the aurora on your way home and a comet next week. It's brilliant.
Thank you very
Thank
much,
you.
Monty. Thanks for closing things up, and we'll catch you later on. Thanks, Dears, as
Thank
well.
you.